last week, we've seen this original application of Kleinman and Winston's graph container theorem on counting the number of C4 free graphs. And the idea there, it's simple but very clever idea is to think of counting C4 free graphs by thinking of how we can generate the graph while maintaining being C4 free, right? And then we generate such graph by adding vertices one at a time, making sure that every time we add a vertex, we don't create a C4, meaning that its neighborhood in the current graph must be an independent set in the square of the graph, thereby linking the number of extensions at every step to the number of independent sets to this square graph. So today we're going to switch, slightly switching the direction of application for graph container and looking at another kind of application, also a very important kind, some sparse analog of classical theorem. This is another main direction where we can apply container type theorem apart from counting results. And we will see why container is so powerful for this type of problem. So first, let's recall two very classical theorem, and then let's see what's the sparse analog. So so another important topic of application of container theorem is the sparse analog of classical theorems. So let's make this rigorous, starting with two very fundamental one. The first one is we know the so let's have some notation. Let's the first one, okay, first one is Mantel's theorem. So the classical results. Mantel says for any n-vertex graph G, which is triangle free, then we know it must have E of G is almost n squared over 4, and this n squared over 4 is optimal because of this two-round graph Tn2 with n over 2 vertices on each side and all edges going between. So in terms of the extremal number notation, this means exn k3 equals to n squared over 4. This is the two-round type. Another classical one is the Ramsey type. This is the Scher's theorem. Scher's theorem saying that if you finitely color, so for any number of colors R, there exists a sufficient large n such that when you color the edges of complete graph Kn with R colors, then we necessarily would see a monochromatic copy of triangle. So for every R, there exists n, depending only on R. Let's say n naught. Such that for any every R edge coloring of Kn n at least n naught contains a monochromatic triangle. For example, when R equals to 2, we can take n to be 6, the Ramsey number for a two-color Ramsey number for triangle. So and what is the sparse analog? What would this type of problem look like? We're going to see these two examples, the sparse analog of the Mantel theorem and sparse analog of Scher's theorem. Basically, the question is, we want to prove such statement, the Turon type and Ramsey type statement, for where instead of the host graph being the complete graph, here we're essentially looking for is a graph G, which is a subgraph of the complete graph that's triangle free. And here we are coloring the edge set of the complete graph. We replace the complete graph by some typical m vertex graph, not the complete graph. So we'd like to go would like to prove this statement with Kn replaced by a typical m vertex graph. And how we do that is basically just by considering random graphs. Okay, and proves this is why we call sparse random analog. Any questions so far? Okay, so the sparse, this typical one, what we're gonna do actually is through, just recall the definition, GMP. This is the Erdős-Rényi binomial random graph. Meaning that you have a vertex that's being n and two vertices I adjacent to j with probability p independent of others. So this is not the single graph, but rather GMP is not a single graph, but rather a probability space. This is a probability space. So here, what we mean by replacing Kn by a typical one, we mean we replace Kn by GMP and understand whether these two statements still hold against subgraph of GMP rather than subgraph of the complete graph. So, question. When do Mantel-Scher's theorem hold relative to GMP? So let's formulate this question rigorously. We have to define this extremal number relative to a different host graph rather than complete graph. So how do we define extremal number relative to a different host graph? Definition. Given a graph G, given a graph, let's say gamma, a different host graph gamma, then we define extremal number gamma no, that's fine. Yes. Given gamma, then we define this to be the maximal number of edges of a graph G, which is triangle free and it is a subgraph of gamma, such that it has satisfied two conditions. G is a subgraph of gamma and G is triangle free. Okay. In this notation, if you replace gamma by Kn, that's our original extremal number. So for example, the extremal number of nk3 is nothing but the extremal number of k3 against subgraph of Kn. All right. In this notation, now we can try to ask what is, so we want to study estimate will be Mantel theorem analog relative to GMP. Well, Mantel theorem is about how large is this guy. Now we're going to replace this by GMP. Okay. Now, what will be a natural guess? The natural guess would be natural guess. If the host graph is everything, is Kn, right? We have Kn here. You have all the edges that's free to choose. Okay, and we're going to choose a subgraph G of Kn that's triangle free. That's the maximum number of edges, this number. Just think of it as a black box, some number there. But now our host graph is not Kn anymore. It's GMP, meaning that every edge of Kn is retained with probability P. So a natural guess would be this maximal, every edge in the maximal is also retained with probability P. So is it true that with high probability, this extremal number, meaning the largest triangle-free subgraph of GMP has size about P times the extremal number of K3. So the natural guess is EX n K3 times P, this factor P. Okay. So this is the natural guess. And then first, I want to leave it as an exercise for you to show that at least lower bound. So to prove this, we want to prove this is roughly p times extremal number of nk3. To prove this, we need two directions, lower bound and upper bound. Lower bound means with high probability, this guy is at least roughly this guy. And the upper bound means with high probability, this guy is at most roughly this. So let's first see the lower bound. Turns out to be easy. So for the lower bound, we will prove that the extremal number so the extremal number, actually, let me prove this. Prove something more deterministic. So here for the lower bound, we don't need the randomness. So for every graph, not just GMP, for every subgraph of Kn, this extremal number with respect to subgraph of gamma is at least 1/2 times E of gamma. Okay. And if you look at this number, which is this is roughly correct, right? Why? If you let gamma to be GMP, then E of gamma is roughly, using concentration of inequality, P times n choose 2. N choose 2 pairs each retain the probability P. So 1/2 of that is roughly 1/2 of E of gamma is roughly 1/2. So let me write it like this. P times 1/2 n choose 2. But this guy is roughly the extremal number for K3. So it's roughly P times extremal number K3. Why is this true? This proof is very simple. We can just take the largest bipartite subgraph of gamma. Consider the largest bipartite subgraph of gamma. And all you need to prove that is that gamma contains the largest bipartite graph with at least half of its edges. This is a standard exercise for you. A slightly harder one, but still easy, is to prove the following exercise. For any graph, not just forbidden graph is triangle. When you forbid, say, a fixed graph H, and for any host graph, subgraph of Kn, prove that the following lower bound. The extremal number for H relative to gamma is at least the two-round density for, so this is the two-round number normalized by n choose 2, so the two-round density times E of G, E of gamma, this lower bound, okay? I'll give you the hint. The proof basically, you want to say in gamma, you can choose a subgraph that has roughly this proportion of edges and being H-free. So all you need to do is to consider a larger such graph that's H, the maximizer for H-free, extremal number for H. Take this graph and then you randomly overlap these with gamma because we overlap them randomly, the proportion of the pairs that becomes an edge, the probability is this. Okay. You can compute first moment methods. All right. Now, using this result or using this exercise, we've already proved the lower bound, as we said. Lower bound is true. It's true deterministically, in fact. So we need to prove the upper bound to finish this problem, to show that this natural guess is correct. So for let's call it question 1. Thus, for question 1, suffices to show the following upper bound. For what P do we have extremal number of the triangle with respect to subgraph of G and P is at most 1/2 plus little o1 times P times n choose 2. Okay? So you have P times the extremal number. Look, here's P times, this is the extremal number, plus some error term. We proved the lower bound already up there. Any question? Okay. Oh, I should say asymptotically almost surely. This means asymptotically almost surely. It means it happens with high probability this bound holds. This will be the translation, a random, sparse random analog of Mantel's theorem. That's the first question. Now let's recall we had two questions, Mantel's theorem and Scher's theorem, the Ramsey for multicolor Ramsey for triangles. How do we translate that to sparse random environment? So instead of coloring the random edges, instead of coloring the edges of Kn, we want to color the edges of GMP. And ask at what threshold P do we almost asymptotically almost surely see a monochromatic copy of triangle. And maybe when P gets smaller, this threshold means above certain P, we with high probability see a monochromatic triangle, and below that, with high probability, we don't see one. So more precisely, let's use this notation. We say that a graph G arrow triangle R colors. This means G is R Ramsey with respect to K3. For any R edge coloring of G, there is this monochromatic of K3. Okay. Then the question would be question 2. For what probability P do we have GMP instead of the complete graph? So Scher's theorem now says in this language that Kn errors K3R when n is sufficiently large, right? So now instead of Kn, we say replace Kn by GMP with high probability, asymptotically almost surely. So question 1 and question 2 are the 2 questions we're gonna talk about today. Let's first look at the random Mantel theorem, the first question. So we need to prove this upper bound. What does this mean? Let's state the statement one more time. With probability tending to 1, the largest triangle-free subgraph of GMP has no significantly more than half of its expecting number of edges, which is P times n choose 2. Okay. So let's first try to prove this using some natural union bound approach. So how do we prove such a thing? We want to prove this happens with probability tending to 1. So let's try to prove its complementary event. That's this extremal number, the largest triangle-free subgraph of GMP, that's significantly greater by delta proportion, more than half of expectation. This complementary event's probability tending to 0. Let's prove that. Okay. So let random Mantel. Okay, let's try union bound. Union bound first try. So let M to be the bound we want to prove are slightly above. So let's say 1/2 plus, do I use epsilon or delta? Let's say, doesn't matter, delta times P times n choose 2. And would like to show, need to show that the probability that GMP K3 bigger than M tends to 0. It's very small probability. Okay. So what does this event mean? Let's try to translate what this means. This means GMP contains some subgraph G, which is triangle free, and E of G is bigger than M, right? Okay. So this means this guy equals to the probability that GMP contains some G, where G is E of G is M, and G is triangle free. Okay. So what we would like to do is to union bound over this. union bound over all. Okay, maybe I should say, let me write it this way. 1 second. There's no big difference, but let me write it this way. This means there exists an M-edge triangle free G such that G is a subgraph of GMP. Let me write it this way, okay? This means GMP contains some triangle free graph with M edges. Now let's use union bound here. So this means this probability is at most sum over all such triangle free and E of G has M edges. The probability, all such graph G, that G is a subgraph of GMP. Okay. So we would like this goal is that this tends to 0. This is small. To have this sum union bound tends to 0, first of all, notice that how many summands here? The number of summands number of terms is at least how many? We have the extremal number. You take the largest triangle free graph, complete bipartite graph. Now inside this complete bipartite graph, you choose M edges out of these. Any choice of M edges. So everything is labeled. You choose M edges. So at least the labeled M edge triangle free graph is at least this much. So that means to have this tends to 0, we necessarily should have at least this term times this tends to 0. Otherwise, there's no hope. But let's do the computation. What is this? Let me do the simplification first. This is roughly, here's the filling the detail for those typing the notes. Prove that, filling this detail, proving that this is roughly natural number E times the extremal number, K3, divided by M, raised to power M, if M is lower order term, subquadratic in N squared. Or in other words, our P is a little over 1. This is the range, okay? If this is the case, then to have this, we must have this term times this probability tending to 0. So let's compute what's this guy. Let me not write like this. So number of terms times this probability. What is this probability? And on the other hand, this probability, what's the colors? No. Is anyone? What's the probability that for fixed G, which has M edges, is containing GMP? The probability is P to the M, right? because G has m edges. Every edge, G has m edges. Every edge is containing P. G and P is already P. So this equals to P to the m. Okay. So times P to the m. This is roughly, using the above estimates, E times the extremal number K3 times P divided by m raised to the power m. So this, if you want this guy tends to 0, we need m is large. Remember, m is this guy. We will need the base to tends to be strictly less than 1, right? To have this goes to 0, we need ex n k3 p to be less than m, which is not true. This is roughly what? Something is strange here. What is this? This is roughly, E is 2.7 something, so this is 1.3 times 1/2 n choose 2 p, maybe. This is roughly this guy, okay? This is roughly 1/2 n choose 2 times E. I merge 1/2 and E, this is 1.3. So left with n choose 2 times P here. But our M is just slightly above 1/2 times P times n choose 2. To have this to be true, we need M to be significantly larger. So we cannot prove the tight upper bound in this naive union bound. You can only prove 1/2 plus, I don't know, what's 1.3? 1/2 plus something. Okay? Some absolute constant, not some delta tending to 0. Okay. Okay. So we need to do something else. The problem here is that the union bound is not sufficient. The number of summoned here, there's simply too many. The problem here, number of terms in union bound too large, too many. How do we do it more sufficiently? Well, this is the container part. So of course we use container theorem. So container theorem in this sparse analog, random analog of classical problem, one of the main reasons that it's useful is because it provides a much better union bound, much better estimate when you do union bound calculation. So let's recall the container theorem. Container theorem for triangle free graph. For every epsilon, there exists a C depending only on epsilon. Such that the following holds. There exists a family of containers F a family of n-vertex graphs such that this is a container for triangle-free graph. For every n-vertex triangle-free G, there exists, let's call it F. Okay, there exists the container F such that G is a subgraph of F. Second thing is the number of containers, there's not so many of them. Which is the family size of family F is at most e to the some constant n to the 3/2 times log n. The third one is that each container is almost triangle free. Yes, the triangle density is very low, tending to 0. This is the reason that container theorem is useful for the number of containers. There are very few of them, provides much better union bound. So let's see the calculation and try to prove this upper bound for an almost optimal range of P. Okay. So this is the theorem first proved by Franco and Rödl in 1986. For every delta bigger than 0, there exists a constant capital K such that the following holds. If P is not so small, remember our naive union bound here, the naive union bound fails to prove 1/2 plus little o1 times P times n choose 2, even when m is little of n squared, meaning when P is little of 1. So as long as when P tends to 0 as n goes to infinity, naive union bound is not working. So here, using container, much better union bound, we can prove all the way to roughly 1/√n up to a log factor. So when P is larger than the sufficiently large constant K times log n over √n, then asymptotically, almost surely, the extremal number of triangle with respect to GMP is at most the P times extremal number of K3. This is what we want to prove, plus some error term. And what will be the order of magnitude of error term? This guy has roughly this many edges. So the error term would be delta times Pn squared. Okay. So to prove this, basically we want to do this union bound calculation. We do the same analysis, but instead of taking union bound over all triangle-free M-edge graph, now we can use very few containers to do the union bound. Let this number to be M. Plus delta n square P. Now we're gonna get containers. So how do we get containers? Well, there's one thing I forgot to say. Here, for supersaturation that we mentioned, for every delta, for every epsilon that we fix here, there exists delta such that as whenever a graph has at most epsilon n cubed triangles, that means the number of edges in this graph cannot be much larger than the extremal number of the K3. So this implies E of f is at most extremal number of K3 plus delta n squared. Okay, this is the contrapositive of supersaturation. So now what we want to do is to apply this container so that each container is almost triangle free. And instead of delta, let's do delta over 2. Okay. Why I wrote the quantifiers wrong. For every delta bigger than 0, there exists epsilon such that if you have at most this many triangles, then your edges is at most this. Okay. So what you do now is apply container theorem for triangle-free graphs with, let's first choose epsilon. We have delta given here. So with epsilon to be depend on delta over 2, this means from supersaturation, this means, and then we get C that depends on epsilon, which essentially depends on delta, because epsilon depends on delta. This means what? We get containers satisfying that each container has at most epsilon n cubed triangles. The number of edges is at most extremal number plus delta over 2 times n squared, because you apply with delta over 2. And then number of containers at most this much, and then blah, blah. Now, let's estimate the same single probability here, this guy. Now the probability that GMP is bigger than this M, right? bigger than the bound we want to prove. Let's rewrite it. This equals to the probability that there exists some triangle-free MHG such that G is the subgraph of GMP. What do we know about such graph? We know that G is triangle-free. That means it's containing one of these containers. So better union bound here. This is M most. Sum over all containers in F. What do we know? Let me write it on the side. G is inside some container F. Now, G is a subgraph of this. This means this event implies what? GMP intercept F, the number of edges, is at least M. At least the number of edges of G, which is M. Correct? This implies this. So it's M most, the probability that E of GMP intercept F is at least M. Okay? Now we just do the number of this, containers here. This is at most. Use standard Chernoff. Number of containers F times, what's this probability? Well, GMP, this is roughly this much above. This is roughly 1/2 times P times n choose 2. P times n choose 2 is the expecting number of edges in GMP. Okay, so when this means we are by a margin noticeably larger than the expectation. By Chernoff, the probability is e to the negative some constant, absolute constant c times delta times the deviation. So this is the probability that for a fixed f, the intersection is at least m. So Chernoff, this is m most, e to the negative absolute constant small c times delta n squared p. Okay, let me zoom out here to see. Well, here maybe I jump a little bit. Why I jump a little bit? The key observation here is that F itself has not too many edges. E of F here, E of F by the last item is at most this. Plus we apply with delta over 2, so delta n squared over 2. So this intersection in expectation should be P times this guy times P times this guy. We are half of this above the expectation. Now, let's just plug in the size of this is e to the c n minus c delta n squared p. But remember, P is at least some absolute constant, some sufficiently large constant K times log n over square root n. So as long as K is sufficiently large in terms of C and capital C, this term is larger than this. So this tends to 0. Okay. That's what we want. Essentially, the only thing that's different here is to use container to do a better union bound. Here. Any question? So the thing we have to look at is how tight is this threshold? We know when K is about 1 over square root n above, up to a log, then the desired upper bound holds. The claim is that when P up to log n, this is actually optimal. So this is not far from optimal. This is the remark. Optimal P would be around 1 over square root n. Meaning, when P is much smaller than 1 over square root n, the statement does not hold anymore. So why? Recall the statement we want to prove. Let's recall it on the side. The statement we want is extremal number of GMP K3 is 1 plus 1/2 plus little o 1. Oops. 1/2 plus little o 1 times P times n choose 2. Okay? So when if P is much less than 1 over square root n, let's use first moment deletion. We will show that number of triangles is much less than the number of edges. Then what we can do? You can do first moment deletion. Meaning we're gonna, for each triangle, appearance of triangle, we delete an edge inside this triangle. And the total number of edges we delete is negligible. So we kill all the triangles while retaining almost all edges. Remove one edge from each triangle. You get triangle-free subgraph of GMP with almost all edges. So let's do this calculation. What's the expected number of triangles? Well, you have n to 3 triples that could be a triangle. For each such triple, by linearity of expectation, you form a triangle with probability p cubed. 3 pairs of edges must be there. 3 edges must be there. So p cubed. This is roughly up to some constant, p cubed n cubed, right? Up to constant. What's the number of edges? This is n choose 2 times p. So order of magnitude pn squared. Now, when p is much less than 1 over square root n, this is much less than that. right? Because this is p squared, much less than p cancel out. Move n cubed to the other side, you get 1 over n. So it's equivalent to this, okay? So this means in this range, we have the extremal number of GMP in this notation is actually 1 minus little o 1 times p times n choose 2, right? For this is the expectation, or here, you just remove a tiny bit. This is tiny bit. Remove an edge from each triangle, you get this. The bound we want to prove is not correct, the constants. So the bound we just proved is optimal up to this log n factor. Later, we will see that this log n factor can be removed by a slightly more careful analysis using this container theorem. But I would like to first prove an almost optimal bound for random Ramsey Sher theorem first. This random Sher theorem is first proved by Rödl and Ruchinsky. It says that for every number of colors R, at least 2, there exists a K depending only on R, such that the following holds. If P is at least K log n over square root n, again, this is tied up to the log n factor. The threshold is roughly 1 over square root n. But this time, the proof of this is not so easy, so let me skip it. We want to prove that when you're above this threshold, up to a log n factor with additional log n factor, we have that GMP arrows K3 with our colors. Then, asymptotically, almost surely, GMP is R Ramsey with respect to triangles. Triangle Ramsey, R colors. Okay. The proof I present here, it's a container proof by Renadolf and Stiger. The idea is to use some Ramsey supersaturation, and then we can make use of containers, again, to do a better union bound in this Ramsey statement. So let's try to prove it. So let's apply container theorem for triangle free graphs to get family of containers F. And the epsilon we take is some sufficiently small constant depending on only on this number of colors R. You take some epsilon sufficiently small with respect to R, we get a bunch of almost triangle free containers F. Now let's try to prove the complementary event happens with probability tending to 0. We would like to show that complementary event means GMP does not arrow K3. This probability tends to 0. Okay? What does this event mean? Let's try to understand what this means. This event means arrow means for any, let's write here, our cheat sheet. This means for every R edge coloring, there exists monochromatic triangle. Does not arrow means we need to flip all the quantifier. Okay, so this means there exists an R edge coloring such that no, there does not exist no monochromatic triangle with no monochromatic triangle. This is what it means. And what does that mean? This is equivalent of saying GMP can be R edge colored with no monochromatic triangle. That means GMP is contained if you take the color class of each one of these R color class, each color class triangle free graph. So the edge set of GMP can be decomposed into R colors of triangle free graphs. So it's a subgraph of G1 union G2 union GR. Each GI is triangle free. Okay? But what do we know about triangle free graph? It's contained in the containers. So this implies that, continue, that GMP, each GI is contained in some container in F. Is contained inside this implies GMP is contained inside some F1 union FR, where each Fi is a container in F. That's what it means, right? So this is a larger event A implies event B, means event B is a larger event. All we need to do is to prove that this event B, a larger event, occurs with probability tending to 0. So now we need to show probability that this event tends to 0. Use union bound over this R tuple of containers. So this probability is at most let's use a shorthand notation. What does this mean? Again, let F bar to be the complement of these R colors. Okay, this is Kn with edges in Fi removed. Is you take the union of these R containers, edges, consider the complement edges, call it F bar. So this event is the same as saying GMP intersect F bar is empty. They don't have any edges in common. Okay. This is our new goal. So far, so good? Yeah, this is the key point. So let's see this key part one more time. What do we need to prove? We want to show that when P is large, with high probability, every RH coloring of GMP induces a monochromatic triangle with high probability. So let's try to prove its complementary event happens with probability tending to 0. Its complementary event means we can RH color GMP so that there's no monochromatic triangle, meaning GMP, its H set can be colored by R color classes of triangle-free graphs. But every triangle-free graph is containing some container Fi. So that means our complementary event, it's a sub-event that GMP, its edges, is contained in the union of R tuples of containers for triangle-free graphs, this event. But what does it mean the edges is contained in the union of R such containers? That means in its complement of this R union of containers, the complementary graph has no intersection with GMP. Okay, we want to prove this is tending to 0. And then here, all we need to do is show, let me copy this, to use Ramsey supersaturation to say that this complementary graph is too dense to miss. What does it mean F bar is too dense to miss? F bar has a quadratic number of edges. So it's unlikely that GMP will have no intersection with quadratically many, a graph with quadratically many edges. So here's the Ramsey supersaturation. I'll call it lemma. Ramsey supersaturation says okay, let me simplify this one more step. What's this probability? This probability is equals to, this is at most, is at most this probability. What is this probability? The sum we have to do union bound over R tuples, and they're a complementary thing, right? So what's the union bound? Sum over R tuples of this, and then this guy intercept F bar is empty. That means an edge does not present in the random graph with probability 1 minus P. And how many edges? E of F bar. Okay, so this is what we want to prove, tending to 0. So now the problem is, let me simplify this one more step. This is at most, the number of choices for F1 to Fr is at most cardinality of F to the power R. simple unit upper bound times, well, this is always true. 1 minus p to the e of f bar is at most e to the negative p times e of f bar. So now the problem is f bar is too dense, we will see omega of n squared. So this term is very small compared to the number of R tuples of containers. Then we are done. Let's see this Ramsey supersaturation. It says that for every coloring, for every R, there exists an epsilon such that the following holds for large N. So what is it? For every R coloring and its complementary graph, so we think of F1 to FR and F bar. Now let's think of F bar as a color F0, all right? So for any phi, how do I write it? Okay. Yeah, okay, let's write it. For any phi, which is a coloring from Kn to, so this is the normal RH coloring. You think of color 0 as the F bar, okay? We have, for every such coloring, either for some color I from 1 to R, it has many triangles. Either exists some I in the color 1 to R such that the ith color, phi inverse of I, has at least epsilon n cubed triangles, or the number of edges of this F0, the phi inverse of 0, is at least extends epsilon n cubed, epsilon n squared. Okay. What this means is that, now let's try to apply this here in our scenario. F0 is, to apply it, Fi is basically phi inverse of I. And F bar is phi inverse of 0. Okay? What do we know? Each container is almost triangle free. We know Fi cannot have at least epsilon n cubed triangles. So the first alternative does not happen. It must have that the number of edges in its complement F bar, the zero's color, is dense. Imply that EF bar is at least epsilon n squared because of container theorem item 3. Okay, this item 3, where is it? All right, so now let's do this calculation. So this calculation, so f to the r times e to the negative p ef bar what do we know about f? F is like e to the c n 3 half log n times this color r tuple r minus p, which is k times log n over square root n times EF bar, which is at least epsilon n squared. So you get epsilon times k n 3/2 log n. This tends to 0 because k is sufficiently large in terms of epsilon, r, and c. But all of these actually depends on r only. Epsilon depends on r, c depends on epsilon, which depends essentially on r. That means we just need k to be sufficiently larger than r is enough. That's what we want to prove. Any question? Let me repeat the idea one more time. To prove that the complementary event happens with low probability, so what does this complementary event means? GMP is contained in the union of R triangle free graphs. But the union of R triangle free graphs is contained in R tuple of containers. What does it mean contained in union of R graphs? That means it has no intersection with the complement of this union of R graphs. But by Ramsey supersaturation, either each one of these R colors has many triangles, which is not the case by our property of containers, or the complementary of this union of containers, which is this F bar, has many edges. So then F bar has too many edges. It's very unlikely that GMP misses this many edges. So the probability is very low. Times union bound R tuple of containers, still it goes to 0. That's the proof. Modulo this Ramsey supersaturation. So for the Ramsey supersaturation, I will just sketch a proof and let you to fill in the details. Okay. The proof is similar to how we normally prove supersaturation. How do we prove supersaturation? We do averaging locally. That when you're above the two-round threshold, you will see some forbidden subgraph. And by averaging, you actually see a positive density of forbidden subgraph. And here Ramsey is the same. You do local averaging, but not by the two-round number. Here now by the Ramsey number, you know that you must see a monochromatic triangle. So either you see many monochromatic triangle, or when you do the local averaging, this part is not a clique to apply Ramsey. Not a clique means there's an edge, there's a pair that's not an edge in color 0. And that means color 0 is dense. That's the idea. So basically do averaging. The idea is averaging. So we know we are given R, right? So let's look at the statement. So, um, so how do we do averaging? When R is given, then let's take M that depends only on R. By Scher's theorem, we know that Km arrows these, right? So we're going to do averaging over M sets. Now this is our Km. You take an M set, uniform random M set. Let's call it U. We have two cases. Let's consider let P to be the probability that what's the probability? What we are given? What we're given is R plus 1 edge coloring of the complete graph. So let's let F to be the union of all the other colors 1 to R. So F bar is just the zeros color. Okay. We let P to be the probability that this random M sets U induce a clique in F. So U induce a clique in F. What's good about it? If U is complete in the first R colors, then we know U has size M by Ramsey. There must be a monochromatic triangle there. Okay, so case 1, if P is at least 1/2 this probability, then we have locally U contains a monochromatic triangle with probability at least 1/2. Then by averaging, this implies a positive proportion of positive proportion of monochromatic triangles, which contradict to the first alternative. So, which yields the first alternative. So some color must have positive proportion of triangles. We have alternative 1. Okay, case 2, if P is less than 1/2, that means, what does that mean? This means with probability positive, well, omega 1 probability, U misses an edge, contains an edge in phi, in the zeros color. But M you should think of it as the constant, n tends to infinity. So locally, we will see a missing edge. This is in color 0. We should think of it as in F bar. Okay, so locally we see a missing edge. That means missing edge has positive density. By averaging, F bar has omega n square edges. We get the second alternative. That's it. fill in the details. Okay. This concludes today's lecture, the random analog of Mantel's theorem and Scher's theorem. Any question? All right, if there's no question, we're gonna continue on Thursday. Thanks for listening.